Hello, this video is going to cover Chapter 8 for our introductory chemistry class. This chapter is called Quantities in Chemical Reactions, and so it's really going to be a combination of the math that we learned in Chapter 6, as well as some of our balanced chemical equations from Chapter 7. So really we're kind of taking those two chapters and putting them together to get to the next step. Now, when we balanced our chemical equations, we did this for a couple reasons. One of them was the law of conservation of mass, but the other one, and I mentioned this in that video, but the other one was it allows us to have a relationship between the molecules or between the atoms. And we call this stoichiometry. So stoichiometry is a fancy way to say that we're doing our chemistry with our math, but let's kind of look at that word and some uses of it. Let me move my face here. I'm going to go right in the middle. So the word stoichiometry literally means element and measure, and so it's a way for us to measure elements or count a mass. And so there's a couple examples that are on here. The bottom left corner, these pictures down here, this is where my dad worked. He retired recently, but him and my grandpa worked at an oil refinery, and crude oil is turned into diesel fuel and regular gasoline and jet fuel. And in order to know how much can be produced, how much heat is needed, stoichiometry is used, and they hire chemists to do that. The next picture over is gold within an ore, and so same idea. In order to know how much gold is in there, how to retrieve it, a stoichiometric process is used. And then the picture above it over here of the Earth, this is the picture of the hole in our ozone layer as of October 2018. And the hole is caused by chlorofluorocarbons. And so there's a reaction occurring between those chlorofluorocarbons and the ozone that has a stoichiometric relationship. And so we can figure out how much of the pollutant has been added into our environment to create that hole in the ozone layer. So it can be used on very large scales, very small scales, but it's a very important tool. And so with that being said, we're going to make some pancakes. And we often use different analogies to talk about stoichiometry because it can be a difficult math concept to grasp. And so we're going to talk about it in terms of pancakes. And here is our recipe. We need 1 cup of flour, 2 eggs, half a teaspoon of baking powder, and with that we can make 5 pancakes. And the idea here is that we can use that recipe as a relationship. So meaning that we have to have the 1 cup flour and 2 eggs and so on in order to make those 5 pancakes. There's a relationship between them. Now, if you want to have more than 5 pancakes, you have to adjust all the other ingredients. You can use the number of eggs you have to figure out how many pancakes you could possibly make. So for example, if you have 8 eggs in your refrigerator, here's the relationship from the recipe. The recipe said that it requires 2 eggs to make 5 pancakes, so we can set this up like one of our conversion factors. Notice the eggs cancel out and we're left with pancakes. So if we have 8 eggs, we could make 20 pancakes. That's our relationship. That's keeping that ratio the same. That 5-to-2 ratio is the same as a 20-to-8 ratio. So we're going to build off of that. If we want to make 20 pancakes, how much baking soda and flour will we need? We already know how many eggs we need. So I'm going to go back and get our relationship. We need half a teaspoon of baking powder and 1 cup of flour for the 5 eggs. So I'm just going to add in here, let's see, we'll just put it up here at the top. 1/2 teaspoon of our baking powder is equivalent to 1 cup of flour, which is equivalent to our 5 pancakes. So we can use that relationship. Any of those two together can become a relationship to solve for a missing piece. So I'm going to start with my 20 pancakes. And we'll figure out how much baking soda we need first. So I'm going to put my pancakes on the bottom because I want that unit to cancel out. And I'm going to put my, oh, I called it baking powder up here. Baking soda. Don't make that mistake. I did that with scones during quarantine. Ooh, they were some gross scones. I'm going to put baking soda on the top up here. And then we're going to fill in our numbers. It requires 1/2 teaspoon of baking soda for 5 pancakes. So I'm going to grab my calculator. So I'm going to do 20 times 0.5 divided by 5, and I get 2. Now our units for this are a little bit different than what we've been working with because we're left with teaspoons of baking soda. But it fits with what we were measuring. All right, let's look at the other one. So again, if we want to make 20 pancakes, I want to know how much flour I need. So in order to make 5 pancakes, I need 1 cup flour. And so I put in my calculator, 20 times 1 divided by 5, and we get 4. Whoops. So again, we check our units, we're left with cups of flour. Now, if you looked at this, especially if you cook or bake, you might have originally, back here, saw that, well, you're quadrupling the recipe. You're multiplying everything by 4. And that's very true. When we look at what we did here, all of our ingredients got multiplied by 4 so that we could make 4 times as many pancakes. And usually if you're cooking or baking, you do this with nice numbers, meaning you cut it in half or you multiply everything by 2. But when we're doing this with chemicals, usually the values aren't as clean, and we're obviously not measuring them by the cupful or the teaspoonful. We're usually measuring them by grams, and so it's not going to be a whole number. So our process is going to be the same, but it's also not something that we can usually do in our heads like you might have been able to see with this one. So we're going to switch over to looking at it from a chemical point of view. Now, we used our pancake recipe to see our ratios. For this one, we're using our balanced chemical equation here. 4 aluminum plus 3 oxygens makes 2 aluminum oxides. So that gives us the ratio of 4 to 3 to 2. So it's not just telling us the ingredients, but it's telling us how many of each ingredient. So it gives us this equivalency or this ratio that can be used within this equation. And we can think of it as molecules and atoms, or because those are very small amounts, we are usually going to think of it as a mole to mole ratio. So this is our ratio that we can utilize in order to figure out how much we could make or how much we need. And we're going to start by doing this with just our moles. So remember this flow chart. This was our flow chart from chapter 6. And so we have the same balanced equation at the top of the slide here, and it says how many moles of aluminum oxide can be made from 3 moles of aluminum. So we know we have moles of aluminum, and we want to convert it into moles of aluminum oxide, so we only need one conversion factor. The only thing we need is that mole ratio. So I'm going to get this chart out of our way. Do a little quick erasing here. So this 3 moles of aluminum, that's my given. The moles of aluminum oxide, that's what I'm trying to find. My conversion factor for this is the ratio from the balanced chemical equation. So whenever we're doing anything within a chemical equation, anytime we're trying to calculate moles or grams, the first step that you have to do is to balance that chemical equation. Now this one's been balanced for us, but you definitely need to check, make sure that your chemical equation is balanced. All right, so I'm going to start with my given. 3 moles of aluminum. And then I'm going to fill in my conversion factors. So I'm going to have moles of aluminum on the bottom, moles of aluminum oxide on the top. And then I can fill in my numbers. I know that from my balanced chemical equation, 4 moles of aluminum can create 2 moles of aluminum oxide. And yes, that ratio could be reduced down from 2 to 4 to 1 to 2. It's going to give you the same numerical answer, so you can leave it the way it is or reduce it. It doesn't matter. So we put it in our calculator, so we get 3 times 2 divided by 4, and we get 1.5. And we make sure that those units canceled out and make sense. Moles of aluminum are canceling, and we're left with moles of aluminum oxide. I do have one more question on here, but I think my writing's going to cover it up a little. Oh, not too bad. How many moles of oxygen will be needed? So we know if we're going to start with 3 moles of aluminum, we can make 1.5 moles of aluminum oxide. But we have one more ingredient, one more reactant up there. We have the oxygen. So if we want to know how many moles of oxygen, that's what we're trying to find, we actually have 2 different options for our starting point. We could start with the moles of aluminum, like we did in the previous problem, or we could start with the moles of our product, the 1.5 moles of aluminum oxide. Either one would give us the same answer. So I'm going to start with my 3 moles of aluminum. And again, I'm going to fill in those conversion factors. We have moles of aluminum on the bottom so that it will cancel out. Moles of oxygen on the top. And I look up here at my ratio. We have 4 moles of aluminum for every 3 moles of oxygen. Put it in our calculator. We have 3 times 3 divided by 4. We get 2.25. We check our units here. Moles of aluminum are canceling out. We're left with moles of oxygen. Now I definitely didn't look at significant figures with these problems because I started with whole numbers. So this was really just a way to set up the problems and show the math with them. But we can convert between any reactant or product and get to any other reactant or product with that mole ratio. Remember, that mole ratio is what allows us to switch from one chemical to the other. Now, most of the time, we're not calculating or counting our quantities by moles. We're counting them by grams. So if we are starting with a certain number of grams of aluminum, and we want to know how many grams of aluminum oxide we can make, we still need to use that mole to mole ratio to convert from moles of aluminum to moles of aluminum oxide, but we got to get in and out of the moles. So we would go from grams to moles using that molar mass conversion factor. And then once we get to moles of aluminum oxide, we can convert to grams of aluminum oxide again using that molar mass as our conversion factor. So the math and the idea behind what we're doing is very similar to Chapter 6, but we're expanding it out to look at an entire chemical reaction and not just within a molecule. So here's our question. Oh, sorry. Too many clicks. How many grams of sodium chloride can be made from 6.8 grams of sodium? Okay, So that's our given. Grams of sodium chloride is what we're trying to find. So if I want to start with grams of sodium and I want to end with grams of sodium chloride, I know to get from one type of molecule to another, I'm going to have to meet at, oh, sorry, I was trying to fix my writing there. It does not look good. That's better. We're going to have to meet in the middle at the moles. So I need to go from grams to moles, and I'm going to use the molar mass to make that conversion. And then I can go from moles of sodium to moles of sodium chloride, and I can use our ratio to do that conversion, and then I can go from moles to grams using a molar mass. Now the one piece of information that we need that's not on here is that ratio, because if we look up at our chemical equation, it's not balanced. So I'm going to make my little list here on the side. It's not underneath like I normally like to do, but we're going to use the space that's on here. So we have sodium and chlorine. The left side has 1 and 2, and the right side has 1 and 1. So I'm going to start by putting a 2 over here. So now they both have 2's, and that just means we need a 2 right there. So it's a balanced chemical equation. We're happy. We know our given. We know our find. We have our pathway to get from one side to the other. So I'm going to start with my given, 6.8 grams of sodium. And I'm going to fill in my conversion factors like I like to do. Grams of sodium, moles of sodium. Those are our conversion factor units for a molar mass. We'll look at our periodic table here in a second. And then I'm going to use my ratio. So I'm going to have moles of sodium on the bottom and moles of sodium chloride on the top. And then that last conversion factor, moles of sodium chloride on the top. So we're going to put moles of sodium chloride on the bottom, grams of sodium chloride on the top, and that will get us to our find. Now, to get the numbers, I have my periodic table. So I know that the molar mass of sodium is 22.990. And that's for every 1 mole. So remember, with a molar mass, it's always going to be 1 mole equals, whoops, there we go. 1 mole is equal to some number of grams. My mole ratio, I go back and I look at my balanced equation. 2 moles of sodium is equivalent to 2 moles of sodium chloride. And then my last one, my molar mass, I know it's going to be 1 mole. And my molar mass of my sodium chloride, I think I have this pre-figured out for us, is 58.44. And to get that, we just use our periodic table. And we're going to add up the mass of sodium and chlorine together to get that molar mass. All right, so now we just put it in our calculator. So when I put this in my calculator, I'm going to do 6.8 times 2 times 58.44. I'm going to write it down. 794.784. And then the bottom I multiply across 22.990 times 2, 45.98. Now this number doesn't really have units. That makes sense because we haven't canceled our units out yet. So then I can do my division, and I get 17.285428. All right, we have a couple things: significant figures, units. So let's talk about units first. Grams of sodium, moles of sodium chloride. We're left with grams of sodium chloride. We started with 2 significant figures, so that's what we need to end with. So I'm going to underline that guy, look behind him, and it's a 2. so it's going to remain the same. So our final answer is 17 grams of sodium chloride. So it takes a little bit of work to get to our answer, but what's nice is that we're going to use the same pattern every time. So even though it can be time consuming, it's very repetitive. All right, we're making some more pancakes. So here's our ratio, our recipe. What if we have 3 cups of flour in the cupboard, 10 eggs in the fridge, and 4 teaspoons of baking powder? This is generally how I cook, especially if I'm making something I want a lot of. I want to make a bunch of pancakes. So the question is, how many pancakes could we make? What's the most amount of pancakes we could make if this is all of our ingredients? So we use each of those starting amounts, the 3 cups of flour, the 10 eggs, the 4 teaspoons of baking powder. Those are all the ingredients we have on hand. We use each of the ratios, so these are the ratios from the recipe, and we figure out how many pancakes each of those ingredients could make. I'm sorry if you hear all that beeping. I think the garbage trucks are in the alley behind my apartment building. Now, the question though is, how many pancakes can we really make? So we can't just make 40 pancakes because we have enough baking soda to make them. We can only make 15 pancakes because once we make 15 pancakes, the amount of flour we have is going to run out. So there's 2 new terms on this slide, limiting reactant and theoretical yield. So we're going to talk a little bit more about those 2 and add in a couple more terms for us. The limiting reactant, also called the limiting reagent, is going to be our ingredient, our chemical, that limits how much product we can make. It's also going to be the ingredient that will run out before everything else. So when we look at our 3 ingredients and how much product or how much pancake they can make, the limiting reactant is the one that can make the least amount of product. Now that amount is the most pancakes we could possibly make. So the 3 cups of flour allowed us to make 15 pancakes, and that's the most we can make because the flour runs out. That amount is called the theoretical yield. So the theoretical yield is this amount of product that the limiting reactant tells us that we can make. So 2 more terms, and then we're going to do some math with this. Now, as you're making pancakes, you might spill some batter, or you might not be able to get it out of all out of the bowl, or you might burn some, or if you're like me, you might need to give one to your dog. My old dog Lucy loved pancakes, but if she had too much and she was full, she would take a pancake and bury it in the backyard and then eat it a few weeks later. So whoever bought my house has a yard full of pancakes and they don't realize it. But because of all of these things, the actual amount of pancakes that we make is usually not the same as the theoretical amount that we could have made. So the actual amount of pancakes that are made is called the actual yield. When we compare how much we truly made to how much we could have made, this is called a percent yield. So to calculate the percent yield, we're going to take the actual yield, divide it by the theoretical yield. So for the examples on here, if we actually make 11 pancakes and our theoretical yield, the amount we could have made was 15 pancakes, our percent yield is 73%. So we're going to do some math with this. And we're going to, oh, sorry, I thought we had So we're onto the math slide. We got a couple more little theory slides here. We have to use stoichiometry to figure this out for chemicals. And we're going to do the same pathway we did on the last one, but we have to do it a couple times, because in order to look at what reactant is our limiting reactant and what is our theoretical yield, we have to do some comparison. This is a good slide of just those four terms: our limiting reactant, our theoretical yield, our actual yield, and our percent yield. And so this is just giving you that quick little summary of each of those terms. Okay, now we're going to do some math. I'm going to move my head down here. Here's our equation. We have two CH3OHs, that's methanol, reacts with oxygen to make CO2 and water. And our question says, if we have 8 moles of methanol and 6 moles of oxygen, what is the limiting reactant? So this one is just based off moles. We're going to start with a little bit of an easy one, and then the next one will be much more complex. So here's what I know. I know how many moles of methanol I have, so this is like knowing how much flour we have. And we know how many moles of oxygen, so this is, I know how many eggs I have. And the question's saying, well, which one of these is going to limit how much product I can make? Which one of these ingredients is going to run out first? And what we have to do is figure out how much product we can make. So the question's not asking about a quantity of product, but in order to know what the limiting reactant is, we have to figure out how much product. And we need to convert them into one of our products. Doesn't actually matter which one, as long as it's the same, because we want to compare apples to apples. So I'm going to convert them both into moles of CO2. So I'm going to start with my 8 moles of CH3OH. My conversion factor here, I'm going to use that mole ratio, moles of CH3OH, moles of CO2. And our chemical equation is already balanced. This has a nice 2:2 ratio, so I can do this math in my head. We end up with an 8 there. We check our units, moles of CH3OH cancels out, and we're left with moles of CO2. Now right now, this doesn't tell us a whole lot. What it tells us is that if we have 8 moles of CH3OH, we could potentially make 8 moles of CO2. And I say potentially because that's assuming we have enough of all of the other ingredients. So now I'm going to start with my 6 moles of O2, and I'm going to have my moles of O2 on the bottom, my moles of CO2 on the top, and I'm going to get my numbers here from my balanced equation. So I'm going to have a 3 on the bottom and a 2 on the top. So we're going to put in our calculator 6 times 2 divided by 3, and we get 4. And we go back and we check our units. Moles of O2 cancel, and we're left with moles of CO2. Now, neither one of these numbers is our right answer, but it's going to get us to the right answer. We compare them. This one's definitely the smaller one. So what that tells me is that my O2 is my limiting reactant. It makes a smaller amount of product. It's going to run out first. It's going to limit how much product we make. So it is our limiting reactant. This number, just so we can give it a title, this is our theoretical yield of CO2 in moles. Most of the time we calculate our theoretical yield in grams, but this is the theoretical yield in moles. The O2 led us to that theoretical yield. So there's always a connection between the limiting reactant and the theoretical yield. So you can kind of think about it as the limiting reactant starts the equation, the math, and we end at the theoretical over here. The other equation right now kind of seems useless, but we needed it in order to do that comparison. Okay, we're going to do the same type of problem, but now we're going to use grams. So it's going to require a lot more work. We have our nickel sulfide reacting with oxygen to make nickel oxide and SO2. We're going to react 11.2 grams of nickel sulfide with 5.43 grams of oxygen, and we have 3 questions to answer. What is the limiting reactant? What is the theoretical yield of nickel oxide in grams? And our third question, if 4.86 grams of nickel oxide form, what is the percent yield? Now we need a lot of space, so I'm going to make our questions smaller up there. I'm going to add one more piece of information right here. We know that our actual yield of nickel oxide was 4.86 grams. That was in the question. I'm just putting it up there so we have that information. So we know the masses of each of our starting materials. We're going to take those grams, convert them to moles of nickel oxide, and convert those into grams. So this is going to be kind of a long setup, but again, it's going to repeat itself. So I'll start with the nickel sulfide, really just because it's written first, no other reason. So I have 11.2 grams of NiS2. I need to convert that into moles. So my conversion factor here is going to be that molar mass. And then I need to convert it over to moles of nickel oxide. Oh, but look what I did. I have my wrong unit on the bottom there. I jumped the gun. Moles of nickel sulfide on the bottom so that they cancel out. Moles of nickel oxide on the top. And then my last conversion factor, moles of nickel oxide on the bottom and grams of nickel oxide on the top. So by the time I finish this, we won't have any answers because we're going to have to do the same thing with the oxygen. And then once we have that, we will be able to answer the first 2 questions. Okay, so I'm going to fill in some numbers here. My molar mass of nickel sulfide, again, we're going to use our periodic table for that. We're going to take the mass of nickel and add it to the mass of sulfur times 2 because there's 2 of them. And I did this ahead of time, so I know that it's 122.83 grams for every 1 mole. Our chemical equation is balanced, so I can look at that to see that there's 2 moles of nickel sulfide for every 2 moles of nickel oxide. And then on that last conversion factor, we need the molar mass of nickel oxide. So I know that it is 74.71 for every 1 mole of nickel oxide. So we put this in our calculator. We get 11.2 times 2 times 74.71 divided by 122.83 times 2, and my calculator tells me 6.81 grams of nickel oxide. All right, I'm going to switch colors here. Well, actually, let's check our units first. We have our grams of nickel sulfide canceling, moles of nickel sulfide, moles of nickel oxide, and we're left with those grams. All right, let's do the other half. So now I'm going to start with 5.43 grams of oxygen, and I do like to line these up right on top of each other like this because we end up with kind of a nice pattern. So I know I'm going to need 3 conversion factors. I need to switch from grams of oxygen to moles of oxygen, and then moles of oxygen to moles of our nickel oxide, and then moles of nickel oxide to grams. And we know some information, especially this last conversion factor. It's going to be exactly the same. We know the molar mass of nickel oxide, so I can fill that in. I know the mole ratio because the equation's balanced, so there's 5 moles of oxygen for every 2 moles of nickel oxide. And then I need the molar mass of my oxygen. So again, I'm going to use my periodic table. I'm going to add up the mass of oxygen times 2. So for every 1 mole of oxygen, we're going to have 32.00 grams. So I put this in my calculator, and my calculator tells me 5.07 grams of nickel oxide. And we can go back and we can double check our units canceling, those grams of oxygen, moles of nickel oxide, and we're left with those grams. All right, so let's use all of this information to actually get some answers. We compare 6.81, 5.07. 5.07 is obviously smaller. So what that tells us is that our theoretical yield is 5.07 grams of nickel oxide. Now the chemical that determined that was the oxygen. So that tells me that my limiting reactant is oxygen. The last piece of the puzzle is our percent yield. So for percent yield, we're going to do actual over theoretical times 100. So my actual was given in the original problem, 4.86 grams, divided by our theoretical that we already solved for, times 100. Put that in our calculator, and we get 95.8%. So to add to my final list of answers down here, my percent yield is 95.8%. There we go. So it's kind of a long process to get to our answers, but as I've said a couple times, notice the similarities. We start by dividing by a molar mass, we use the mole ratio, and then we multiply by a molar mass. And that pathway stays consistent. We're using that stoichiometry roadmap that we've used in a couple problems already. So the last topic in this chapter is looking at enthalpy. And enthalpy is a type of energy. It's the amount of heat that is associated with a reaction. And the heat can be released in a reaction. This is called an exothermic reaction. The heat can be released. This is called an exothermic reaction. And I like to think of it as, instead of saying the heat's being released, we could say the heat is exiting, because it helps me remember exo and exiting. And in an endothermic reaction, the heat is entering. Enthalpy is abbreviated with a delta H, and if the reaction is exothermic, then delta H is going to be a negative number, and if it's endothermic, delta H will be positive. So there's a couple graphs down here, and we've seen these graphs in other chapters, but with an exothermic reaction, the reactants are going to start out at a higher energy level than the products, so the amount of energy that we are decreasing by is our delta H. And the opposite's happening in an endothermic. So the reactants are at a lower energy, the products are at a higher, and so we have to go up in energy, and that amount that we're going up is that delta H value. And we can associate a specific amount of energy with a reaction. So on the bottom here we have C3H8 plus oxygen makes CO2 and water. C3H8 is propane, so this is the combustion of propane, and it tells us that this reaction has an enthalpy of negative 2,044 kilojoules. And we can use the ratio within our chemical equation over here to solve for a certain amount of energy, or a certain amount, how much mass produces a certain amount of energy. And we can use those same stoichiometric relationships to calculate that energy. So that's our last problem we're going to do today. We're going to use that same equation, and our question says how much heat is released in kilojoules when 155 grams of oxygen are combusted. So we know we're starting with grams. I'm going to convert that into moles. We're going to use the molar mass for our conversion there. And then I can convert that directly into how many kilojoules, because there's a relationship between the amount of oxygen and the amount of heat in the reaction shown. One more thing to point out, this is a negative value, so that tells me that this is an exothermic reaction. And that doesn't change. We need to include that sign when we do our math. So I'm going to start with my given, 155 grams. Oh, that did not look like a G. Grams of oxygen. And I'm going to convert that over to moles. So grams of oxygen into moles of oxygen. And then using my balanced equation, I'm going to go from moles of oxygen into kilojoules. So let's fill in our numbers. 1 mole of oxygen is 32.00 grams. Again, that's straight from the periodic table. And then I'm going to use that balanced chemical equation. So for every 5 moles of oxygen, 2,044 kilojoules of heat are released. So when I say that they are released, that's why we get that negative number there. So I'm going to put this in my calculator. 155 times negative 2,044 divided by 32 times 5. 1980.125. All right, we're going to do our checks. Grams of oxygen, moles of oxygen, we're left with kilojoules. We want to check our sig figs. We started with 3, so there's 1, 2, 3. It's going to stay in 8. So 1980 kilojoules. Now that 0 at the end is a little ambiguous, so it's best to rewrite it without that 0. So I'm going to rewrite it as 1.98 times 10 to the third. Let me show you where that third comes from. So there's our decimal. We're going to move 1, 2, 3 places. And when I rewrite it without that 0, that's showing me that I have 3 significant figures. And there's my kilojoules. If we wanted that 0 to be significant, if we needed 4 significant figures, then we would include the 0 there, because now it's after a decimal place and it is showing us that it's significant. All right, that is it for this chapter. We're definitely going to do some practice in Zoom. I highly suggest doing practice on your own. Do a bunch of them, and it will feel normal, and it will make a lot more sense than just watching somebody else practice. All right, thank you.